Hello everyone. Today we'll be talking about molecular bonding and its relationship to the geometry of the molecules. We'll begin talking about how do we draw Lewis dot structures and then how we use them to find the electron domain and molecular geometry. I have often seen students getting confused between these two terms, but actually Lewis dot structures helps us to find the arrangement of the electron domain, and that helps us to find the molecular geometry using VSEPR theory. We'll do a lot of practice today on Lewis dots, so you can pause the video and practice the structures or try on your own before you see me showing the answers. I'll also walk you through the Lewis dot structures for polyatomic ions. I'll introduce you to two important concepts: formal charges and resonance. And then finally, we'll spend some time together using VSEPR theory to find the geometry of the molecule. So what are molecular compounds? When two nonmetals share electrons to make a covalent bond, that is called as a molecular compound. Now each element wants to have an octet of 8 because that's what makes the molecule or the element stable. Below are the list of elements you see here with their dot structures showing their valence electrons. We are going to use them to draw the Lewis dot structures. Now let's take our first example of chlorine. It's a diatomic molecule. It comes from group 7A, so it's going to have 7 valence electrons, and it needs one more to have octet of 8. So there's going to be sharing happening among these two electrons, which I can also draw by a line. Okay, now let's check the octet. This I'll call this as the first chlorine and call this as second chlorine. The first chlorine had 7 electrons of its own. The 8th one is coming from the second chlorine. And the second chlorine also now has 8 electrons, 7 of its own, and the 8th one is coming from the first chlorine. Okay, and this line that I have drawn here between two chlorine atoms, this line actually is also called a single bond, and it represents bonding pairs because at each end of it we have an electron that's being shared. Okay, so let's talk about methane. It's one of the easiest structure to draw. Carbon comes from group 4A, so it has 4 valence electrons in its outermost shell, and hydrogen comes from group 1A, so it has 1 valence electron. Now remember that hydrogen always is drawn at the terminal or outside, and that's because it only needs 2 valence electrons for a full outer shell. Yes, there are exceptions and they can make an octet with just 2 electrons. Okay, so I'm going to start placing my carbon with 4 valence electrons, and I'm going to draw hydrogen atoms placed around it symmetrically. And we're going to see a bond formed or electron share between this carbon and this hydrogen. Similarly, between this valence electron of carbon and hydrogen, and similarly here as well as here. Now let's check. Carbon gets an octet of 8. 4, it already had its own. Fifth coming from this carbon, fifth coming from this hydrogen, sixth coming from this hydrogen, seventh from this hydrogen, and eighth from this hydrogen. So carbon gets an octet of 8, and hydrogen is also happy because it also has an octet of 2. Okay, so as we go into more complicated structures, there are certain guidelines that we follow to draw the Lewis dot structures, which I have explained as we go forward. Okay, also there are two ways of drawing the structures, as you can see here. It could be a line like I have shown here, or it could be a dot that I have shown here. But make sure you follow one of the two pattern, not both. Okay, now some structures just make single bonds, like we saw the example of chlorine. Some structures share two pair of electrons and they make double bonds. We're going to see example of oxygen. And some share three bonds and make triple bonds, which will be the example of nitrogen shared in the next slide as well. So we can have multiple bonds as well. And after that, I'm going to introduce you to the guidelines and steps that we follow in order to draw the Lewis-Strauss structures. The next example we're going to see is oxygen, and we'll see a double bond happening in a molecule of oxygen. So oxygen comes from group 6A, and so it's going to have 6 electrons in its outermost shell, and it needs 2 more to have octet of 8. So these 2 electrons are shared, and then these 2 electrons are shared, right? And so I would call this as oxygen 1, oxygen 2. The first oxygen had 6 electrons of its own, 7th and 8th coming from the second oxygen. And similarly, the second oxygen had 6 electrons of its own and 7th and 8th coming from the first oxygen. Okay, so this is an example where we can show a double bond in a given structure. Similarly, a structure of nitrogen molecule shows triple bond. Nitrogen is coming from group 5A and has 5 valence electrons, so it needs 3 more to have octet of 8, right? And so if you see, both the nitrogens end up having an octet of 8. Now, as we move on to more advanced structures, there are certain guidelines that we follow to draw these Lewis structures, and we have to follow these steps in order. The first one is to find the total number of valence electrons in our given molecule. The second is that you draw the skeletal and connect them with a line, or basically with a bonding pair. Then you will find your remaining electrons based on how many you have used in the second step. And then you will distribute your remaining electrons to each connected atom so that each gets an octet of 8, except hydrogen. Remember, hydrogen can have only octet of 2. Then the fourth step is to, out of the remaining electrons, you take them and now place them to the central atom. Okay, so at this point you want to double check your work and make sure that your terminal atoms and your central atoms has an octet of 8. Now step 5 is important because in some Lewis-Strauss structures we use step 5 and in some we don't. So what happens if you run out of all your electrons in step 4 and you have nothing left to give to the central atom, and your central atom doesn't have an octet of 8 yet? When you reach to that situation, at that time you borrow a lone pair of electron from a neighboring atom, and that will result in a multiple bond, which could be a double bond or a triple bond. Let's do some examples to see how this works. Okay, now let's take our example for water. Uh, our first step is to find the valence electrons. It has 2 hydrogens, which is 2 electrons, and oxygen has 6 valence electrons. So our total electron comes as 8 electrons. The second step is we are going to do the setup or draw the skeletal. We know hydrogens are always terminal, so I'm going to have hydrogen on the sides, and then I'm going to connect the atoms. Now this is the bonding pair. So remember, at each end I have an electron that's being used. So I have used 4 electrons, right? And so I'm going to subtract 4 electrons, which I'm going to call as bonding electrons, and my remaining electrons comes as 4. Now the third step is to distribute my remaining electrons to the neighboring atoms so that each gets an octet of 8. But in this case, we have hydrogen, which can only hold maximum of 2 electrons. So we don't have to distribute anything to hydrogen right now, and we can move on to the next step where we distribute our remaining electrons to the central atom. So we have 4 electrons, so we write that 4 electrons around oxygen. Now these electrons are not participating in making a bond, and these are called as lone pair. Lone pair means the electrons that are not used for bonding. Now I want to talk a little bit about the geometry of the molecule. Many times I have seen students drawing a structure of water in this way, like I drew earlier. But actually the correct structure of water is drawn in this way. It is bent, not linear like that. And that's because these electrons that you see here, the electron pair that you see here, the electrons have electron cloud around them, which causes the electrons to repel, and they want to go as far as possible, and this causes these bonds, these bonding pairs to bend, and they get compressed. You see the connection here, how Lewis dot structures is telling us about the bonding and about the lone pair of electron, but it doesn't tell us the shape. Okay, we still start by drawing the Lewis dot and then determine what bond angle we're going to get, and that helps us to determine the molecular geometry. So in the next slide I have shown you a demo to explain the geometry a little better. Hope you like it. Hi everyone. The right way to explain this would have been using a molecular kit, but I don't have that at home right now. So I've used some oranges and marshmallows to show you the model. The orange is representing the oxygen and the marshmallows are representing the hydrogen. I have seen in the class students draw a structure of water something like this, but actually this is wrong. The right way of drawing the structure of water is this. Let me explain you why. Well, in water, we have 2 lone pair of electrons and we have 2 bonding pairs. Now, electrons have electrons cloud around them, because of which there is repulsions happening and they want to go as far as possible. And because of that, the bonding pairs are further compressed and pushed down. As a result, the structure looks something like this. Bent. Okay, we have the lone pair of electrons here. You can see they are at quite a distance away. The bonding pairs are at quite a distance away from the lone pair of electrons, and the angle that happens to be between the bonding pairs is 104.5 degree, and that's what actually geometry tells us. So I hope this helps to understand the structure of water. Okay folks, I think we're running out of time. I would advise you to go over the video and practice the structures again, and also try to draw the structures of the molecules I have listed below. In our next class, I will be sending you the solutions of these structures as well. If you have any doubts, just email me and I can definitely arrange a Zoom session and explain or take your doubts. And also please keep checking your Canvas for upcoming announcements. Have a great day. Thank you.